We need like the mass, right, out of this thing. So let's try to gather as much information as we can to come up with our differential equation. We need a 32-pound weight. So the weight is equal to 32 pounds. And so do you remember how to find the mass out of this? Mass is equal to weight divided by gravity or something like that. Equals weight divided by gravity. And so that's 32 pounds divided by the gravity is 32 feet per second squared in this system. So this is one slug. Remember slugs? UCSC slugs. The weight stretches a spring 2 feet. What does that piece of information do? No. It's a spring constant, right? So spring constant. And then I think it's just 2, right? Do we need to do Hooke's law? All right. So Hooke's law says that 2K, what's Hooke's law again? What? Negative kx. So what's the So I think the one with lambda is the friction, and I think we're gonna ignore the damping forces there, so we're not gonna have any damping forces. But we need to find K. You sure it's not just 2? You guys remember how to do this problem? All right, so we're trying to find K. We have M. M is equal to 1. And I think the only thing we need is K. And then no damping forces, so was it lambda it's called? What? K should be 16. So the force is the number of pounds, 32. And then K, and then X is the distance, and so stretching, pulling it down, which is going to give a positive value. So K is equal to 16. So M is equal to 1, K is equal to 16, and we don't have any damping forces, so lambda is going to equal to 0. And so how does our equation look like again? We use X or Y? X of t? This doesn't matter. X double prime plus lambda X prime plus K over M X. Is it 2? And then this is equal to any external forces that we might have. All right, so we got lambda to equal to 0. We got K is 16 and M is equal to 1. So our differential equation is X double prime. I should use Y, huh? Oh well, I use X. plus 16 over 1 times x is equal to f of t. Now, f of t in this example find the equation of the motion x if an impressed force f of t acts on a system from 0 to 5. So we have an external force, 20t, that's acting on this system when t goes from 0 to 5, and then after that it turns off, and then it's removed. So there's some external force that's moving this spring, and then it disengages, and then so now it's just going to be up to the regular motion of the spring. This happens when t is bigger than 5. Okay? And so we have been studying, we've been studying something. Laplace transforms and unit shifts in the t, s and t. So this is a shift in the t, which means we're going to need to create some sort of unit function with this. Yeah?
Just to note that equals f, at least looking at the book, was uppercase f, which is equal to the lowercase f being the actual force divided by the mass of the...
Oh, we need to divide by the mass
it's
also?
1 here, so we're
Okay.
we're fine, but...
They call it capital F? Capital F is, especially when they're talking about Laplace transforms, capital F is like a weird choice for them. Normally they call it G or something.
So it was the force function divided by the mass, which actually is 1.
Yeah, which is good. All right. So, what we need to do is we need to recall that we had a way to set up and rewrite our piecewise functions in terms of a special function called the unit step function. Is it 0 and 1 or 1 and 0? Yeah?
So if the mass was not 1,
Yeah, if the mass wasn't 1, then you have to divide your function by whatever that mass is. So does our unit function start with 0 or start with 1? Is this 0 and then 1? Oh, sorry. Maybe I should t minus a. 0 as long as my t is less than a, and then 1 if t is bigger than or equal to a. So this is our unit step function. And so what we need to do is we need to rewrite our piecewise function as a unit step function. And since this is kind of backwards, it's not 0 first, it's 0 after a certain amount of time, there needs to be some sort of subtracting going on. So I don't know if you guys memorize the formula. There's a thinking process for you to come up with a formula. I can't think of it right now. So I'm just going to look at the formula. All right, so let me look at the formula for that. Our step function, this is the general formula. There's simpler formulas if it's zeros and stuff like that, but here it's assumed that it's g of t and h of t. So it looks like the first function here minus that function times this thing plus the h function. Okay. So fortunately, in our problem, our h function is equal to 0, so we just have two terms that we're going to be concerned with. So just for reference, we'll put that here. So we can write our function to be the first function here. That's 20t minus the first function, 20t, times the step function, the unit step function, and then it takes the step at 5. And then plus, if this was non-zero, then we would say that h function times the unit step function again. But it's 0, so that just goes away. So now we have a function in what we would say closed form that we can transform or translate into Laplace world. Okay, ready? Let's see, is this going to fit here? Yeah, let's just take this one more step to translate into Laplace. So now we're going to be in the S world. All right, so the derivative, I'm using x now instead of y, so that's just a minor thing. So I have S matching with the order of the differential equation times capital X. Remember, when you go into the Laplace world, you capitalize your variables, your dependent variables. And then there's this x of s here. I'm going to drop this parentheses s in the next step, but I'll write it here for the first one. Minus s times, we need our initial conditions. X of 0 minus x prime of 0. So that's our x double prime. I might need to write this a little bit lower here and make more room. And then now I have a 16 times x, so that's just x. And then now let's translate our right-hand side into the S world. The t transforms to 1 over what? S minus a. So what's a? I think it's just 1 over s, right? So the exponential functions are s minus whatever. This one? 1 over s squared. Yeah. All right. Now, this next one, how does the transformation work for the unit step function again? You remember? So, but we need the function in the t world to be of a certain form, right? So here I made a Laplace basics document where it just has Laplace. I guess that's not very good. What? So here's a transformation theorem over here that says that we need to get our function looking like a t minus a also. And so that makes our job a little bit trickier. And so what we need to do is we need to rewrite this 20t times u of t as, let me do this in blue since we're still in a t world, as 20t minus 5. I'm going to take out the minus 5 for right now. And write this in a different color. So what I need is, I need to rewrite this as a 20t minus 5 so I can transform it into the S world. But since I'm subtracting 5 here, I'm really subtracting, what am I really subtracting? 40, what? 100? So minus 100, I'm really adding 100, and then times mu of t minus 5. To make it even more confusing, there's a negative in front of this whole thing. So, just like transforming back from the S world to the T world, when you transform from the T world to the S world, you need to have your, especially if there's a shift in the T, you need to have your F also kind of corresponding with the shift. So I just have 20t, that didn't have a corresponding shift, so I need a 20 and then t minus 5. So in this parentheses, or big brackets, I need to now to transform this. So I have this 20 over here, this 20 over here, and then now I have this shift, E, or the t minus 5 times u of t minus 5. Okay, so that's like a shifted t with the unit shift, the unit step function. So I need to translate this t to the S world. And how does t translate? T translates as 1 over s squared. So it's going to be 1 over s squared. But then because there was a translation in the t, we have to include this exponential function. Let me rewrite this a little neater. So e to the, what's the shift? 5. So e to the 5s or negative 5s? The shift is the negative as, right? So the shift is positive 5. So here e to the negative 5s. So that's the first term. The second term is a constant. And then just doing the regular shift is just e to the negative 5s. And then what? Is this good, or do we multiply by something else? 1 over s. Right? Is that okay? No, not for some people. I don't know. Yeah, so when you do the unit transform by itself, there's divided by s involved. Another way to think about that is that this is 1 times a unit transform, and then it's the unit, the Laplace transform of 1 is 1 over s. Okay? Yeah?
If I have 2 functions multiply and I apply the transformation, then I get separate between the
No. So you can do that when you're adding or subtracting, and you can even do that if you're multiplying by a constant. But if you're multiplying sine and cosine together, for example, you can't take the Laplace of sine and the Laplace of cosine and multiply it. So you can only do that for special occasions or special functions, and one of them is this unit step function. So the unit step function has a special transformation. But before you can use that transformation, you have to make sure that the function you're multiplying it by also has a shift of t minus 5. So you have to be careful about that shift as well. All right. So now we have that. Now we have this function in the S world. We're in the S world, and we're going to try to We're in the S world, and we're going to try to solve for x, capital X, and then transform it back. All right, so this is the algebra stage. So this whole right side's a big mess, but I'm really just concerned about getting x by itself. And so, we need to figure out, we need to figure out our initial conditions. Ignore any damping forces, use a graph. If the weight is released from rest at equilibrium, so these key terms here, from rest at equilibrium. From rest means it's not moving when you start. So x prime of 0 is 0. And then at equilibrium position means your starting position is also 0. So that makes a little bit, makes our job a little bit easier, that the initial conditions are 0. All right, so back to our problem. Initial condition 0. These are gone. And those are all initial conditions, so those are all we're able to knock out. So what do we have left in our algebra? We can factor out an x squared or an x. And I'm going to not write of s here. And then this will give me a chance to simplify this a little bit. I think I might be interested in keeping all the exponential functions together and then work it out that way. So I'll keep this separate, 20 over s squared, and then minus, I have this thing, 20 s squared, I'll put big brackets there, 100, 1 over s. So I have a feeling I'm going to have a shift function. Because I shifted this, right, I'm going to have a shift function on the way back when I translate it back. So this is going to be my shift function. And now I have to divide everything by s squared plus 16. So my x function is equal to, I'll write 20 on the side, 1 over s squared plus 16. So I'll be interested in splitting this up. Minus, I wonder if I should combine this and then split it up. Let's combine it. So s squared is the common denominator. And if I combine this, I'm going to get 20 plus 100s. Is that correct? Did I do that correctly? Made it into one denominator. And I divide by s squared plus 16. We could, but then, we'll factor and simplify again. All right, so I'm not interested in trying to do this by hand, so I'm just going to use Wolfram Mathematica to break these things apart. Apart square free, what? Apart, so I have 20 divided by 20 20 divided by s squared times s squared plus 16, which is an irreducible quadratic. So I get this for my first fraction, 5/4 times 1 over s squared minus 5/4 times s squared over 16. So I might need to do something with the second one, but the first one looks good. The second one, I'll split that one apart as well. And that one has a 20 plus 100s in the numerator. And then the same denominator, s squared. So this one I'm going to need to work with this as well. So let's take pictures of these. That's our first one, which we'll work with. And then the second one, it's inside the parentheses, so I still have that exponential on the outside to deal with. So, just for trying to work some of these things out, if I have an s squared in the bottom, then my numerator should be 1, right? If I have an s squared in the bottom, n is equal to 1, my numerator is going to be 1 factorial, which is 1. So in terms of transforming the first one, I'm pretty good with this. I'll just rewrite it as 5/4 times 1 over s squared, and then that'll transform to t. The second one, I have 5/4, and then I have s squared plus 16. So the s squared plus 16 is like s squared plus 4 squared, right? And if I have this, and if I have a constant, I don't have an s on top, I have a constant. I want my constant to match up with this 4. So I would need to multiply by 4 over 4. And that would give me a 16 in the denominator. So a 5 and 16 in the denominator, and then I have a 4 over s squared plus 16. Okay? So these are the little things you need to do for Laplace transforms. These coefficients are important. All right. Same for this one. And let's see. The first one is a 5/4 1 over s squared, and there's going to be a shift for that. So we're going to take a look at that shift later on. And then we have 25 over 4 times 1 over s. Then we'll have the shift for that as well. So now this is the tricky part right here. This one has an s squared plus 4 squared again. And then this one has an s on top and a constant that you're adding. So we need to split this up into 2 different fractions. So I'm going to try to do the work up here. We got 5/4, negative 5/4. And then I'll split this up into a 1 over s squared plus, what? I don't know. Maybe call that a 25? Just talking to Christopher about little mistakes that you would make in the middle of the problem and screw up the rest of your work. Yep, so that's a 25. All right, now let's go back over here. We got 1 over s squared over 4, s squared plus 4 squared, and then plus 5s over s squared plus 4 squared. So that's this fraction that splits up into 2. And now the first one, I want a 4 on top. So I need to divide this by 4 also. So the same reasoning here, I'm going to get a 5 over 16. So it's 5 over 16 times 4 over s squared plus 4 squared. And now I have this. The second one gets multiplied by negative 5/4. So let's take that work over here even further. This one times this is negative 25 over 4, and then s over s squared plus 4 squared. And I think that's okay because we just need an s on top, right? This will be, is the s on top the sine or cosine? That's the cosine. The one with a constant on top is a sine. So this is a cosine. And then that's our constant, negative 25 over 4, and then s over s squared plus 4 squared. And throw that e to the negative 5s as a shift. So we're shifting these 4 functions over here is going to have a shift. Okay, so let's take it back to the t world, to the real world. Let's see how our solution might look like. All right, 1 over s squared, that translates back into a t, right? So we have 5/4 t minus 5 over 16, and this translates back to sine, cosine, sine, and then there's a coefficient here, so that coefficient is 4, right? Sine 4t. Now the shifts. We have a negative, so it's this thing times the exponential function. So when you have transform times the exponential function, it translates back to whatever this is with a unit shift of 5. So this is, we'll put a 5/4 here. And then this translates back to a t, but there's a shift of 5. And that's how the first one transforms back. Is that cool? So I think we did all the hard work in the green. The algebra was easy, and then this is a little tougher to try to make it look like try to get it ready to transform back. And so that was the hardest part in the algebra. I mean, it's still algebra, but that was the hardest part. So once you do that, you're just transforming back, and you got these in nice forms already. This one transforms back. Let's put that negative sign in front, and this transforms back to just 25 over 4 times 1. There's no shift on the 1, but there is a shift for that function. And then now we have this. So let's be careful of the negative. There's a negative and a negative, so we'll call that a positive 5 over 16. And here's our function. This is, again, the sine function, 4 times t. Now, instead of t, there's a shift involved, so we'll have to do a t minus 5 with the unit step function. And then the last one is 25 over 4 with 25 over 4 with the cosine 4 times t, and then the t now is shifted with a unit step function. Wow. Oh yeah, positive. There's negative here and negative there, so that makes them to a positive. Okay, there you go. They asked us to graph this. I don't know if I want to graph it. Let me see if I can graph it. Just give myself 3 minutes to do this. Oh boy, what is... need help already. Piecewise. So type X, Control Shift F. Select all, Control Shift A. All right, let's see if I can remember that. So I'm going to define my unit step function f of x equals 0, Control Shift F, if 0 less than x less than 5, Control Shift A, no, Control Shift A, another branch, Control Shift A, and then 1, Control Shift F, if x is bigger than 5. All right, so let's see. This is 5/4. Y equals 5/4 x minus 5 over 16 sine of 4t, 4x minus 5 over 4 t minus 5 f e x, and then minus 25 over 4 times f plus 5 over 16 times the sine 5 over 16 times the sine of 4 times x minus 5 times f of x plus 25 over 4 times cosine of 4 times x minus 5 times f of x. All right. Where's t? Got it. All right, so let's see if this makes sense to us. You have a force, you have this oscillating spring, and then you have an external force that's pushing it, and it gives a force of 20t. So it's going to keep pushing it lower. So it's trying to oscillate, but it's forcing it to follow this 20t path, right? So it goes up, and then after 5 seconds, you take away that force, and now the graph is going to act on its own. So acting on its own, then you just have this going on forever. There's no damping force, so it's not going to damp down, and it's going to oscillate indefinitely at this amplitude. So that kind of makes sense, and so this looks like it's a good graph to examine. So let's take a picture of it and put it in our notes. By the way, I did this using a computer, using a graphing program, and then use some other pieces of information. But if you're doing this by hand, it's not impossible. It'll be hard, but it's not impossible. But what you can do is that you can look at the different pieces of the piecewise function, and the different pieces are this thing combined with this makes one piecewise function. And then this thing combined with a sine makes another piecewise function. It's not a coincidence that the coefficients are the same. You could take that out and look at it as one piecewise function. And then after dealing with that, you just have a couple of other piecewise functions that you can string together and add on. So you can put these together as a piecewise function. So in fact, this first one over here, if you combine this one and this one, so that function is going to look like basically t minus t minus 5. So that's just t, I think. With the 5/4 out in front. So you can combine those functions in pairs to make your piecewise function look more readable as a piecewise function that you studied like in pre-calculus or something. You can combine those two, and then, like I said, the other two functions over here can be done separately. Or if you can work out a way to do this using a graphing calculator program, and you can define your unit step function separately, you know that you're just multiplying the unit step function. So that's another approach to do that. Okay. Wow, that took a long time. All right, let's move on. The next section talks about some other operational properties that I don't really care too much for. One important one might be this convolution property, where if you're multiplying two functions in the t world and you want to transform that into something in the s world, then there, you know how. So I guess let me just take a quick picture of this, but I'm not going to talk about it in detail. But I should say something, a little something about this. We know that if we have f of t plus g of t in the t world, and then we transform this using Laplace transform in the s world, this is capital F of s plus capital G of s. We know that it's linear. Because it's linear, then there's scalar multiplication business. Addition and scalar multiplication would hold. But unfortunately, if we have a product of two functions, transforming this into the S world is not f of s times g of s. It's not necessarily, that's not how it works. Now, we have a couple of multiplication of two functions. Like if one of these is a step function, then we have a property for that. If one of this was an exponential function, then that's like, it's like one of the shifts. I think it's a shift in the s. So we can deal with that if one of these functions is an exponential function or a shift function. But if this is sine times cosine, or if this is t times cosine or something like that, then we're going to have a harder time dealing with that. So the way to deal with that is the combination of the convolution and the convolution theorem. And so that's how you might be able to deal with a product of these things. All right? And here's another example of a product. If you're multiplying it, if it's not an exponential, but if you're multiplying with a t, then that's actually equivalent to a derivative. Now, this is an interesting theory, but this is something that I don't really care to talk about too much. And I don't think there's a section 7.4 in your homework, right? So I kind of skipped over that. And if you guys want to look through it, you can look through it and try out some of the problems and look through the examples. But I'll just skip that and go on to the other one is a little bit more interesting. So let's go to section 7.5 and talk about another special function. So to me, there's two special functions in terms of Laplace transforms. And one is the unit step function, and the other one is called the Dirac Delta function. So let's take a look at that. Now, the Dirac Delta function is a weird function, or it's weirdly defined. And different textbooks define it slightly differently. But a lot of them rely on the idea of a limit, and they define it using a limit. So here they define it using a couple of properties. One property says that the delta function at t sub 0 is equal to infinity at t sub 0 and 0 everywhere else. So that's like a weird definition. The other definition, the other part of this property, is part of the definition, is that the integral over all the real numbers of the Dirac delta function is 1. So the other definitions that you might see, or maybe it's presented this way in the book too, but sometimes people look at the Dirac delta function as a limit of something. And they start off with with so on your x or your t-axis, at some point t sub 0, you start off with this area of this. You start off with a square that has 1/2 on the left and 1/2 on the right, and then height of 1. So the area of this thing is equal to 1. And what they do is they shrink it down, not shrink it down, but they shrink down the base and then now keeping this area to be equal to 1, they make the base smaller, and so to try to keep the area of 1, this thing has to go up with a larger height. And then if you keep going in this process, if you make this smaller, then your height is going to get bigger if you make the base smaller. And so what happens is that this function is defined as a limit by letting this distance over here go to 0, and that makes your height go to 0. And so it actually looks like, if you want to look at it this way, it looks like just a stick. So at infinity, this is t sub 0. It just goes up, and it goes up, I guess to infinity. I don't know how to draw that. It just goes up forever. And the idea there is that it looks like it's just one point, and technically it is, but the area is equal to 1. The area over this whole thing is equal to 1. So that's like a weird thing. How does that look like in real life? Or how does that mimic something in real life? One way to think about this is that you have that spring. This is the problem that we've been working on. You have that spring problem with a mass attached to it, and it has an oscillating force. So we have an external force that takes this into the sine, or that example that we did, 20t. We have an external force. That does something to this. Well, what if your external force wasn't a constant moving force, or it wasn't a functional force that moves from 0 to 5 or from 0 to pi or something like that, but instead your force is, how should we put this, is a hammer that whacks it one time, pow, right? So you take this hammer, so you do something with a spring, you do something, you release it, and at some point you whack it with the hammer. And so that hammer is going to give this force at one instant in time, and then that's it. So that big force at that one instant of time is like that delta force. Ooh, delta force. It's like that delta function that's imparting this one big force. Does it go all the way to infinity? I don't know. It depends on how hard you hit it. But let's assume that you hit it hard enough so that it has this seemingly infinite value that you're putting on at that one instant in time. And so that one big force is the Dirac Delta function at a particular time. So you can think about it as this spring at rest, and then if you whack it once at the very beginning, so that's going to be your delta function at t naught is equal to 0. So that can start this spring moving if you hit it at the very beginning. Or if you start this spring moving and then at some point, let's say t is equal to 5 seconds later, you decide to hit it 5 seconds later, then that could be the force that happens at delta t minus 5. Okay? So that's like the delta, that's what the delta function is. I guess more importantly, in our context, we want to be able to do a Laplace transform for this. So we need the Laplace transform for the delta function. So the transform for the delta function is this. So depending on what T naught is, if you have a delta function in your differential equation, that will transform to e to the negative s times T naught, whatever that T naught is. I guess I should have said T naught times s, because T naught is a constant. That's the time that you hit this thing. And an interesting fact is that when T naught's equal to 0, the Laplace transform is 0. Is that right? What? Yeah, I think this should be 1. My notes might be wrong. Anybody have their book open to this? I don't know what page. 7.5.1, Theorem 7.5.1. Yeah, it's 1, sorry. Makes a difference. Let's make sure this is fixed up in our notes here. Because T naught is equal to 0 makes your transformation e to the 0, which is equal to 1. All right, let's see how difficult or easy or difficult this might be. First couple are first order linear differential equations. We can solve for that pretty easily. Should we do that one, or I don't know, pick a number between 1 and 5? I don't have 5. 1 and 4? Number? 1 and 4? 4? Why? Let's do this one. We got y double prime plus 16y. Hey, this is like the other one we just did. Is equal to the delta function with a delta 2 pi. All right. We got nice conditions here. So imagine this is a spring. That spring that has the same scenario, that 32-pound weight that we had on the spring, that had a spring constant of 2, or the spring releases offsets at 2 feet. And so we got that 16 business over here. And then you leave it alone, so the initial conditions are 0 and 0, so it doesn't look like it's going to move any. And then at time t is equal to 2 pi, you decide to whack it, and then it's going to do something. All right? So now that we got that, can you have that visual there? It's doing nothing, and then you whack it at 2 pi, and then it's going to start oscillating. And there's no friction here. There's no y prime component, so there's no friction. So it looks like it's just going to oscillate after you whack it. So let's see how this is going to work. Let's solve for this using Laplace transforms. Let's transform this already into the S world. Let's take our Laplace transform. We got s squared capital Y minus s times y of 0 minus y prime of 0, which are all equal to 0, so we can get rid of those, plus 16 times y. That's just y without any fancy transformations. And now we have this delta function at 2 pi. So remember, this transforms to e to the negative s times t naught, which is 2 pi. So I'm just going to say 2 pi s. Okay? So we got zeros for these things, so that makes an easy problem. Finally, got y, and then we have s squared plus 16 is equal to this. And so this is just y is equal to e to the negative 2 pi s times 1 over s squared plus 16. Now, this is almost ready to transform back. But I have an exponential function in my s world, and you know how that transfers back, right? That transfers back as a shift in the t world. Remember? And it's going to transfer back as a shift in the t world. So let's figure out how that shift is going to work out. So we have a constant coefficient here of 2 pi, so that's going to be our shift, right, in the t world. So the t world shift is going to be t minus 2 pi. So 2 pi is your shift, which means I'm going to need, well, I don't need anything from here. But I do need to match the coefficient here. So this is 4 squared. So I need a 4 divided by 4. So this thing will transform back as a sine function. All right, transform back using inverse, and so we have y of t is equal to, let's get rid of that 1/4, deal with that right now. And then the shift is that this becomes a sine function, sine of 4 times the shift, t minus 2 pi, times the u function, t minus 2 pi. So what is this? The t minus 2 pi business over here, if we distribute this, this is 4t minus 8 pi. And the minus 8 pi is a shift of 8 pi. And when you shift it by 8 pi, even if there's a coefficient here, the shift of 2 pi isn't going to do anything, right? If you shift the sign by 2 pi, it's going to look exactly the same. So we can just call this a 1/4 sine 4t times u of t minus 2 pi. And the u function is 0 in the beginning, right? And then, so up to 2 pi. Up to 2 pi, it's going to be 0 in the beginning, and then after that, it's going to be 1. And then we take our 1 and we multiply it by 1/4 sine 4t. So that's your function. And this one is easy enough to graph without a help of a graphing program. So I think this is just going to be 0 up to 2 pi. And when you get to 2 pi, it gets whacked, right? And so now it begins oscillating. It has an amplitude of 1/4, and it has a period of whatever the period is, 2 pi over b. So 2 pi over 4, pi over 2. It has a period of pi over 2. So that's how it is, and that's pretty much how we imagine the system to work, right? Because there are no initial conditions. Initial conditions, you start at the equilibrium, and you're not hitting it. You're starting it at rest. And so if that starts at rest, then nothing's happening. And then all of a sudden, you whack it with a delta function. So at that one point, it begins oscillating, and it just oscillates the way it's supposed to oscillate. Okay? So think about the delta function as a big whack. All right, that wasn't too bad. So there are all these rules about shifting. The exponential function in the t and exponential function in the s means there's a shift on the other side. And then the delta function has that shifting ability happening from the t to the s. All right, let's see. What else should we talk about? We have a bunch of examples here. Oh, that's it. I don't know. Should we do another one, or are we good? So the thing to do is to practice this. I see a lot of faces that aren't very excited. What the hell's going on kind of face. And so that's because I'm kind of jumping back and forth and referring to a lot of the theorems and ideas that we've done before. So when I say that you have to try to match up the numerator with the k in the denominator kind of business, when I say that when I expand the second derivative of y, you know, all this stuff was in my head already, so I just write it down, but it comes from this theorem. When you do a translation, or when you have a translation in the s, it gets translated back with an exponential function in the t world, and then vice versa. If you do a translation in the t world, it comes back with a translation in the s world, with an exponential in the s world. So all these ideas have to start coming naturally to you when you're doing your homework. You know, try to do your homework, and then try to, you know, have this page of notes handy right in front of you, so that you're referring back to it instead of flipping through the pages in the book. Nessa? Well, the unit step function is defined to be 0 and 1. So now the thing is that if you're multiplying this by something on the side, then I don't. But in terms of your unit step function, it's always defined to be 0 and 1. And the thing on the outside here is what makes this into whatever else. And so, in fact, if this g was equal to 0, and then h is just h, then the g's are equal to 0. And so you have exactly what we had in our last example, that 1/4 sine 4t. And so that just means the bottom one becomes 1/4 sine 4t. And so those are, that's the association. So when you talk about the unit step function by itself, it's 0 and 1. So it's called a unit, meaning 1, and then everything else is 0. The way to not make it 1 is to multiply that function by something on the outside. Anything else? Practice. So it's practice and practice and practice. So this is not something that you can look at and put away and then study right before the final exam. You have to practice and be comfortable with a lot of the different rules and translations that are happening to make this really kind of second nature to you. All right. Yeah. Say it again. Is this in web access? The what? No, these are my notes. I don't put my note. Well, so the web access, I put the notes that you see up on the screen in the slides, and so these would be the slides that you would see in web access, but my notes are my notes. But I put clippets in my notes here, so that's how that works. I could sell it to you. No, or my notes. All right. So happy Thanksgiving. Good luck with working. Keep working on this Laplace transforms. Vanessa asked me how this is going to be translated into a test. I'm going to think about that over break, and so I don't think I'm going to ask you to start from a very beginning to a very end of a problem, especially if there's a lot of these like partial fractions that you have to do. So I'll probably give you pieces of the work to solve in an exam situation. So I'll talk more about that next time. Happy Thanksgiving.